All right, so last time we did modular curves with the complex numbers. Today we're going to talk about modular forms and Hecke algebras, still over C. So I want to start by talking about, I'm going to talk mostly about modular forms of level 1 and then say a little bit how they generalize the higher level. So we have this picture, the upper half plane mod gamma 1, root of gamma 1 was just SL2Z. This was in bijection with the set of lattices in C, modulo homotheti. And for today, I'm going to call the set of lattices in C, I'm going to denote this by script L. I'm going to use it quite a bit. And this was in bijection with the set of isomorphism classes of elliptic curves. And I named this space Y1. And we said that looked like A1. So we have all these different descriptions of basically the same thing. And let me recall how some of these maps went. So this isomorphism here is the J invariant. This here is a definition. This one takes a lattice lambda to the elliptic curve C mod lambda. And this one takes a point Z in the upper half plane to the lattice that I called lambda sub Z, which is what's generated by 1 and Z. And recall that if gamma is an element of SL2Z, and we write it as ABCD, then when I do lambda of gamma Z, so gamma of Z is that linear fractional transformation, but this is just CZ plus D inverse lambda Z. So this is what shows that two things in the same SL2Z orbit give homothetic lattices. So that's why this is a well-defined map. All right, so a modular function is a function on the moduli space. It's meromorphic. I guess I'll say a function on Y1 that's everywhere meromorphic. And I mean at infinity as well. At this missing point, it should be meromorphic. And so the J invariant is an example of such a function. It's holomorphic everywhere except at this cusp at infinity. It has a simple pole there. And I mean, since y of 1 or x of 1 just looks like P1, its field of functions is just generated by this J thing. So these things are all just rational functions in J. So this maybe is kind of the most natural concept to think about functions in this space, but we're not actually going to use these as much. We're going to use a sort of related thing called modular forms, which are perhaps a little less intuitive, but they're better to work with. So I'll give the definition of those now. So the idea is that a modular function you can think of as a function on lattices, which is invariant by homothety. Modular form is going to be a function on lattices which is not invariant under homothety, but scales in a predictable way under them. But it also has a holomorphic condition. It's supposed to be everywhere holomorphic. So here's the definition. A modular form of weight K is a function, say f, from the set of lattices to C, such that it satisfies three conditions. So the first is that if you apply a homothety to your lattice, so scale by alpha, that this is supposed to pull out with an alpha to the negative k. So the second condition is that f should be holomorphic. And by that I just mean that the function on h that you get from f is holomorphic. So the function z maps to f of lambda sub z is a holomorphic function. And the third condition is that it should be holomorphic at the cusp as well. And the way that I want to phrase that is that as you let z go to I infinity in the upper half plane, this limit exists. And we'll call that f infinity. So that's the holomorphic at infinity condition. And I'll write M sub k for the space of these things. It's a vector space. And then there's a variant which is called a cusp form, which is also just defined now. So a cusp form is just a modular form that vanishes at the cusp. It's modular form f by this definition such that f of infinity is equal to 0. And I'll write sk for the space of them. That's also a vector space, it's a subspace of MK. All right, so the first thing that I want to do is give several different ways to think about modular forms. Oh, I guess I should have said, well, I had that up there. So if we have one of these modular forms, I defined it as a function in the lattice, but I'm going to let, for z in the upper half plane, I'm going to define f of z to be this. And so this means that this will let us switch back and forth between thinking in terms of lattices or in terms of points on the upper half plane. And you see that if you do f of gamma z, then this is going to be f of lambda gamma z, which is f of, so I said that this thing was cz plus d to the minus 1 lambda z. And then the modular form, the homogeneity property means that this pulls out by cd plus d to the k. I'll just write f of z. So in fact, this function f on the upper half plane transforming under SL2z in this manner is the same thing as it defining a function in the space of lattices which transforms in the right way. So this is already two different ways that you can think about modular forms. They're kind of homogeneous functions on lattices, or they're functions on the upper half plane that transform like this. Are there any questions so far? Okay, so these things are functions on this moduli space, the moduli space of elliptic curves. So it'd be good to interpret what these things mean in terms of elliptic curves. So the first thing I want to talk about is what the modular interpretation of modular forms are. All right, so we have this space of lattices L. And over this, you can think of the trivial vector bundle C. So this is just C times L. And now for each point in here is by definition a lattice in the C. So you can form the quotient. So you get this family of elliptic curves. The fiber over lambda is C mod lambda.
Wait, what's that map from C to C mod?
So this is the trivial vector bundle over L. So this is C times lambda, it's the projection map. Sorry, C times L, it's the projection map. And sort of in the fiber over lambda here, you have a natural lambda sitting inside this C. And that's what it is by definition. And this is this kind of family of elliptic curves over L. Okay? And so I'm going to let W be just a parameter on this C. This is the identity map from C to C. So we get this differential dW. And it descends down to the quotient. right? So this gives the global, a global holomorphic one form on this quotient. There's only one dimension of them, and this is one of them. So for each point down here, we've defined a global holomorphic one form on this elliptic curve over it. But this thing is not sort of compatible with homothety. So if alpha is in C star, then alpha defines a map from L to L, just by homothety it defines. And if you pull this differential back by alpha, that's like multiplying by alpha on these C's, it's just going to scale the differential by alpha. So we have the C star group acting here, and the quotient is kind of the moduli space that we're interested in, but this dW is not invariant under the scaling, because it scales by what you're scaling by. So it doesn't descend. But what you can do is if you have a modular form, so if F is a weight K modular form, then if you do F times dW to the K, this is invariant under homothety, because F scales by alpha to the minus K, and this dW to the K scales by alpha to the K. And that suggests that it should descend to the quotient. So there's some subtlety here because the quotient's a stack, and so let's kind of not worry about that too much. And let me just say first kind of what should happen and what actually happens if you work with stacks, but I think it doesn't quite work if you don't. But then I'll say what it is more concretely. So let pi be the universal family over y1. So this is the universal family of elliptic curves over the space of elliptic curves. And I'm going to define lowercase omega to be the push forward of the sheaf of relative differentials. Are you worried about this thing here? This is just a notational problem. I mean, I don't know how to say this in a nice way. This is a trivial vector bundle, and we have some like family of lattices inside of it. Yeah, yeah. It's not good notation, but yeah. Yeah, this is just a family whose fiber over lambda is that elliptic curve. That's on it. Okay, so, right, so we push forward this sheaf of relative differentials. So this is, it turns out to be, this is a vector bundle on E, on Y1. And its fiber over a point E is just the space of one forms on that elliptic curve. Maybe I'll call this script E. It's the universal family. So the fiber of this omega at an elliptic curve is just H0 E omega 1. And so what this computation is saying is that, sending an elliptic curve to this thing, if I send a lattice to this thing, that's invariant by homothety, so it should descend. So if I have a modular form of weight k, I should be able to build this element of the kth tensor power of H0 E omega 1 for each E. So F dW to the k defines a section of omega tensor k over Y1. And in fact, this is a bijection. Any section comes from an F, as long as, you have to impose some condition at infinity of the right kind, which I'm not going to talk about today, but when we talk about the modular interpretation of infinity, I'll talk about that. But this means that you can identify modular forms with the sections of this line bundle over this Y1. right, so let me kind of say how this works in a more concrete way. Well, it depends what the condition at infinity is, right? And you might have to allow some. All right, so let me say this in a more concrete way. So suppose we have a modular form of weight k. And E is some elliptic curve. And suppose we have some non-vanishing one form on E, which unfortunately I'm going to call omega. So I can pick an isomorphism of E with some E lambda. I mean, this I mean C mod lambda. And then I can look at this thing. I can evaluate my F on this lattice, multiplied by dw of the k. And this expression is invariant under homothety. It's well defined. So I can think of this as a well-defined element here. It's independent of the choice. On the other hand, there's another element that we have in there, which is the kth tensor power of this omega that we've picked. And this is a one-dimensional space. So the first thing is just some multiple of the second. So I'm going to define f of E omega to be the quotient. And so this thing, F, has two properties. Well, first, it's invariant under isomorphism. So if there's an isomorphism of E omega with E prime omega prime, meaning an isomorphism of curves which takes one form to the other, then the values of these F and the two are the same. And the second, so this is property one, and property two is if you scale omega, right, then it's just going to pull out that scalar in a natural way. So alpha times omega is alpha to the minus k. F of E omega. And then there's also some holomorphicness condition, which I'm not going to go into. So this is basically describing just what a section of this kth tensor power of omega looks like. It's just a rule that assigns to every elliptic curve and one form on it some number and scales in these ways. So this is kind of the modular interpretation of modular forms. This is what they mean in terms of the modular problem. Are there any questions about this? All right, so I'm going to do some examples in a bit, and I think this point of view is kind of a nice way to think about things in certain cases, and I think you'll see why then. But I want to say a few more things before I get to those. So the second, I want to give another kind of similar interpretation of modular forms. Again, it's going to be sections of some line bundle. So, all right, so if we have a modular form on the upper half plane, then, like we've said, it scales under SL2Z like this. And so a simple computation shows that if you pull back the differential form dz on the upper half plane, that this is just cz plus d to the minus 2 times dz. So let me show you how this works. This is easy. So this thing by definition is just d of az plus b over cz plus d. And so we figure that out just by taking derivatives in calculus. So this is a over cz plus d minus az plus b over cz plus d squared. And then we multiply this guy by cz plus d over itself. So we get a times cz plus d. Oh, there's a c here, from the c here. Minus c times ab plus b over cz plus d squared. And now the coefficient of z in both things is ac, so the z's go away. And then we have ad minus bc, which is the determinant. We're in SL2z, so that's 1. Okay. All right, so that's why dz behaves like this. And so you see if we multiply our f by an appropriate power of dz, then the scaling factors are going to cancel again. So if we assume that k is even, so say f has weight 2k, then f times dz to the k is invariant under gamma. And so that means that it defines some section, which I was calling omega, of the kth tensor power of omega 1 on x1. Well, it defines a meromorphic section. It might not be holomorphic. And here's how you can sort of figure out the local properties. I mean, here's how the local properties of this omega relate to the local properties of f. Now you can see what holomorphic and meromorphic conditions you get. So suppose you have some point in the upper half plane, and that y be its image. I'll call that pi on x1. All right, so you can look at the ord at y of omega. So you know the size of its zero or pole. And this is related to the order of x as follows. So you get 1/2 times the order of x times the order of f at x minus k, if x is the point at I. You get 1/3 the order of f at x minus 2k, if x is this point rho, the 6th root of unity. You get the order of f minus k, if x is infinity. And you just get the order of f if x is not any of these 3 points. All right, so let me just prove the first one. The other ones go very similarly. All right, so let me say that z is a local parameter on h, the upper half plane at the point x at I. And let me say that w is 1 at y, so on x of 1. So these things vanish to order 1 at these points. So the projection map pi, so pi is the map from h to y1, or h star to x1, is ramified with ramification at x2 at the point I, because we have this stabilizer group. So if I pull back w, it's going to look like z squared plus higher order terms. Right, that's what ramification means. And so if I pull back dw, I get d of this, so I basically get z dz plus higher order terms. And so if we say that the order at y of this omega is n, right, that exactly means that you can write omega in terms of this local uniformizer. It's w to the n times dw. So when I pull it back, pi star of omega, so when I pull back w to the n, I get z to the 2n. Oh, sorry, this is dw to the k, or weight k form. And when I pull back dw to the k, I get z to the k dz to the k. And this pullback is, I mean, by definition, f dz to the k. And I said that this thing's descends. I mean, you can write it as the pullback of something down below. And so this shows that locally f looks like z to the 2n plus k. So 2n plus k is the order at x of f. And so now if we solve, we subtract off k, divide by 2, and that's what we get. Okay? So this just comes from the local behavior of the quotient map. But this is really useful because now we can actually compute something. So here's a corollary. So mk, so remember this is the, or m2k, this is the space of modular forms of weight 2k. We can identify this with sections omega of omega 1 to the k on x1, which is just p1, that satisfies certain local properties. So such that the order at, let's say, pi of I of omega is greater than or equal to minus k over 2. Right, we want our f to be holomorphic at I, so that means we want the order of f to be greater than or equal to 0, and that's the same thing as asking that the order of the descendant thing is greater than or equal to minus k over 2. And similarly, we want the order at pi of rho to be greater than or equal to minus 2k over 3. And we want the order at infinity to be at least minus k. And everywhere else we want to make it be holomorphic. So I basically said the proof, but let me say it again. So, and what I said before was that there's a sort of bijection between, well, maybe meromorphic things on the upper half plane. Forget the holomorphic condition. So meromorphic things which transform like modular forms on the upper half plane, and meromorphic sections of this bundle on x1, and the bijection, relates the orders like this. So if you want f to be holomorphic, that's equivalent to asking that the order of f is greater than or equal to 0 everywhere, and that just translates into these equivalent conditions on the other side. And there's a similar thing with cusp forms. You just want them to vanish once more at infinity. Right? But this is useful because now we can compute the dimension of M2K, because we know how to compute the dimension of line bundles on P1 very easily. So corollary, the dimension of M2K is the floor of k over 6 plus epsilon, where epsilon is 1 if k is not 1 mod 6, and 0 otherwise. And let me explain how this works. So let me name some points. I'll call P pi of I and Q pi of rho. And I'll just write infinity for the image of infinity. And let me look. Let me put n to be the floor of k over 2, and m to be the floor of 2k over 3. So this previous corollary was just saying that M2K, and you can just write this in a different way. It's the space of global sections on P1 of the kth tensor power of omega 1, twisted by some divisor to allow poles at various places. So you're allowed a pole of order n at P, and a pole of order m at Q, and a pole of order k at infinity. so this bundle here has degree, well, the degree of omega 1 on P1 is minus 2. So when I take its kth tensor power, it has degree minus 2k. And I just add to it these numbers that I put in here. So it's n plus m minus k. And so as long as that's at least 0, which it is as long as k is non-zero, then the dimension of m2k is just going to be 1 plus the degree. And then now you just simplify. So 1 plus the floor of k over 2 plus the floor of 2k over 3 minus k is just happens to be equal to that. All right, so for example, the dimension of M2 is 0. Because for M2, I'm taking k to be 1. And so the floor is 0. And since k is 1, epsilon is 0. But M4 through M10 all have dimension 1. And then M12 has dimension 2, because the floor of k over 6 plus epsilon is 2. And the dimension of the space of cusp-forms is always just 1 less, because you're just asking one condition, but it vanishes at infinity. So the dimension of Sk is 0 for k less than 12, and the dimension of S12 is 1. All right, so let me do some examples now. Are there any questions first? Okay. All right, so suppose that we have a lattice. So we want to define, to build a modular form, we need to somehow associate to a lattice a number, so that when I scale the lattice, I scale the number. And the easiest way to do that is to just sum all the elements of the lattice up. Right? Because then if I scale the lattice, all the things are just going to scale by the same amount, and that'll pull out. Of course, you can't just sum all the elements of the lattice, because, yeah. But you can sum, 1 over elements of the lattice to some big power, and then that will converge. And so that's the idea. So suppose you have a lattice, and k is some number that's at least 4. Then put gk of lambda to be the sum over elements of lambda. And this prime here means I don't want to sum over the 0 element of 1 over lambda to the k. All right, so you can show that because k is big, this thing has good convergence properties. So you don't have to worry about any of that stuff. And this obviously scales in the right way, right? I mean, gk of alpha lambda is clearly alpha to the minus k gk of lambda. So it looks like it's going to be a modular form. And now we just need to check, the holomorphicness conditions. So remember, I'm defining g of z to be g of lambda z. And this thing is clearly just the sum over integers n and m, not both 0, of 1 over n z plus m to k. Because those things are my lattice elements. And of course, each one of these terms is a holomorphic function, and I'm summing them up, and the convergence is good, so the result is holomorphic. So this is holomorphic in Z. And furthermore, as you go to infinity, so naively, if you let Z go to infinity, this is going to go to 0 if n is not 0, right? Because the denominators are going big. So, and that works out because convergence is good. So this is the sum over non-zero, sorry, where n is 0, where m is non-zero, of the terms without an n. And this, oh, I didn't say it, k is supposed to be even. I mean, you have both lambda and minus lambda, so if k is odd, then every term cancels and you get 0. And that's true generally, that there are no modular forms on gamma 1 of odd weight, they're always 0. So this k is even, so the minus ones are the same as the plus ones, so this is just twice the Riemann zeta function of k. So that means you have this holomorphic condition at infinity. This is gk. Okay, so this says that gk is a modular form. And we know it's not cuspidal because the zeta function is not 0. Of weight k. And so for k less than 12, this is every one of them, because we know the dimension of the space of modular forms is 1. And in fact, it's true that, well, if you multiply two modular forms, you get a modular form and the weight adds. And it's a fact that G4 and G6 generate the ring of modular forms. So in a sense, you know all of them, but this description usually isn't extremely useful. So there's a related series, Ek is often defined to be 1 over 2 zeta k gk. So this is called the normalized, this gk is called the Eisenstein series of weight k. And this one's called the normalized Eisenstein series. And its value at infinity is 1. All right, so a general thing that happens is if you have a modular form, then it's invariant by z goes to z plus 1. I'm thinking of this as a function on the upper half plane, and this transformation comes from the element here. And so this means that you can write f, so f is a function of e to the 2 pi I z, which is usually called q. So you can expand to f into powers of q. And this is called the q expansion or the Fourier expansion. And the condition that f is holomorphic just means that these a n vanish for n less than 0. And cuspidal means that a0 vanishes as well. I mean, I define it to be that as you go to infinity, the thing converges. So, I mean, if you look at this series, if z is in the upper half plane. So this e to the 2 pi I z, you have I times something with positive imaginary part. So this q is always less than 1 in the upper half plane. And as z goes to infinity, the q goes to 0 very fast. So in this series, all the positive terms are going to die, and the negative terms explode. So if you want it to be nice at infinity, you need no negative terms. All right, so the Q expansions of these Eisenstein series are nice and important. I'm not going to prove it, but I'll state it. So ek of z is 1 minus 4k over the Bernoulli number, bk, times this series. So here, b is the Bernoulli number. And that's defined by x over e to the x minus 1 is the sum of bkx to k over k factorial. And this sigma guy is the sum of divisors function. So you can prove this by what's more or less a formal manipulation of power series. All right, so these Eisenstein series are sort of the first example, and in a way they give everything. Right? I said they generate the ring of modular forms. But another important one, which you can express in terms of the Eisenstein series, is this delta, which is E2 cubed minus, or sorry, E4 cubed minus E6 squared. So both of these things have weight 12. So this is a modular form of weight 12. And both of these guys, the E4 and E6, are equal to 1 at infinity, because we normalize the constant terms. And so this difference vanishes at infinity. So we get a Cuss form. And we know that the space of Cuss forms with the weight 12 is one-dimensional. We previously computed that, so this looks like it should be it. But of course, you need to know that it's non-zero. And you can see that by computing with these Q expansions. So using this, so you just have to look at the constant in linear terms. Just look at the, the constant term goes away, so look at the linear term. You see that delta is Q plus higher order terms, so it's non-zero. So this means that delta is the unique up to scaling Cuss form of weight 12. So the Q expansion of delta is a complicated thing. There's no constant term, and then the other coefficients are called Ramanujan's tau function. And there's not like a nice expression for them, just some complicated thing. But there is a nice product formula for delta, which I'll tell you what it is. This is due to Jacobi. And so that delta is Q times the product of 1 minus Q dn. And so, of course, you can expand this product to get the Q expansion series for delta, but that's a complicated thing to do. All right, so the second thing I said today was how you could interpret modular forms in terms of the modularized interpretation of width of curves, and I want to go back to that now and explain how these Eisenstein series and delta work from that point of view. So let me write EAB for the elliptic curve y squared is x cubed plus ax plus b. So we've talked about this before. Recall that every elliptic curve is isomorphic to one of this form. Every elliptic curve over C is isomorphic to EAB, to some EAB. And we have an isomorphism. We have a natural isomorphism, phi, I'll call it, from EAB to E u to the 4 times A, u to the 6 times B, where u here is a non-zero complex number. And that's just defined by taking x to u squared x and y to u to the cubed y. So I'm going to let omega AB be the one form dx over y on this curve. This is a holomorphic one form. And so this phi map, I said it took x to u cubed x and y to u squared, x to u squared x and y to u cubed y. So when you plug that in here, you get a u squared on the top and a u cubed on the bottom. So if I pull back by phi, this omega 1 here, I get u inverse times the omega 1 here. All right, so this means that given a pair E and omega, there exists a unique AB such that E omega is isomorphic to EAB omega AB. Right, because once I pick an isomorphism with EAB, all I'm allowed to do is use these U's to change to different ones like this. And that's just scaling this omega AB. So if I pick an isomorphism of some EAB, my omega is going to be off from omega AB by some amount, and you use that as your U to move to the correct EAB. And so I can define a function on pairs E omega. I'll call it F4, or maybe I'll call it E4 prime. So E4 prime takes this pair E omega to A, this A here. And E6 prime is going to take it to B. And I can define delta prime with E omega to be the discriminant of EAB. So if my E omega is isomorphic to EAB, then if I scale omega by U, it turns out that you scale these guys by not that, but U inverse. So E U to the minus 4A, U to the minus 6B, whatever. And so that means that E4 of E U omega is e to the minus 4 times E prime 4 E omega. And with a 6, it scales in the same way. And delta squares with a 12, of course. So these things are all modular forms in terms of the description I gave in terms of moduli theory. And these match with the E4s and E6s and deltas that I defined previously, up to some scala. I didn't compute the scala. So. So this is a nice way of thinking about things. I mean, we had these Weierstrass equations, and a problem that we always ran into with them was that they're not canonical and not well defined. A is not a function of the elliptic curve. But this gives you a sense in which they are. I mean, this A you can really think of as a section of this bundle, like omega 1 tensor 2 on the moduli space of elliptic curves. Are there any questions? All right. So far we've been talking about modular forms of what's called level 1, invariant into the full SL2Z. So we're going to need something a little more general. Higher level modular forms. So basically everything I said carries over in some way to an arbitrary finite index subgroup. For some applications, we need to assume that gamma contains gamma n. So we say that gamma has level n. It contains gamma n. So that's where this word level comes from. Okay, so let me just quickly go through the basic definitions in this situation. It's very similar to before. So a modular form of weight k for gamma is a function on the upper half plane that satisfies three properties. So first we want the same transformation law. F of gamma z is cz plus d to the k f of z for all gamma in our group gamma. We want F to be holomorphic on H, and we want it to be holomorphic at the cusps. So let me elaborate on the last condition, holomorphic at the cusps. So F is holomorphic at infinity if this limit exists. And then at the other cusps, you can translate by an element of gamma 1 to move them to infinity and get the defining condition. So precisely, if x is some other cusp, then you can write x as gamma times infinity for some gamma in not the group of interest, but in SL2Z. And then you can define g of z to be cz plus d to the minus k times f of gamma z. So here this gamma is ABCD. And G is a modular form of the same weight for the conjugate group, gamma inverse gamma. And F being holomorphic at X, the same as G being holomorphic at infinity. And so I'll write mk of gamma, the space of modular forms, weight k for gamma. and sk of gamma for the cusp forms. So here cusp form means that it vanishes at every cusp, not just at infinity. So f is a cusp form if it vanishes at every cusp. All right, so you can interpret these things in terms of moduli theory similar to before. So mk of gamma can be identified with sections of this kth tensor power of what I call omega. I guess I didn't say this before, but this is called the Hodge bundle. Sections of this bundle on x gamma, or maybe I'll say y gamma with certain conditions at the cusps. And again, this means something concrete. So it means that you can, so f defines a function which takes in an elliptic curve and then some auxiliary data, right? These x gamma parameterized elliptic curves with some kind of n torsion structure, and a one form to some complex number. And it should have the same homogeneity as before. I mean, it's exactly the same thing as I just did in level 1, except it also can be, depend on this auxiliary data. So this question mark here is like, this is a point of order n if gamma is gamma 1. It's a subgroup of order n, cyclic subgroup of order n. You're using gamma 0 n. Similarly, you can think of these kind of geometrically as sections of a bundle on the modular curve, well, in a slightly different way than I described them now. So if k is even, so wait, 2k modular forms correspond to sections of the k tensor power of omega 1 on x gamma with certain local conditions. Right, in the level 1 case, we saw that weight 2k modular forms corresponded to sections like this, and then at I and at rho, we needed some local conditions on the valuations. So you can work out exactly what those conditions are in general, but there's one case where it comes out very nicely, and the answer is important. So, most important case. I'll state it as a proposition. So cusp forms of weight 2 for gamma correspond to holomorphic differential forms on x gamma, everywhere holomorphic. So this means that the dimension of the space of weight 2 cusp forms is the genus of x gamma. And that, I think you can prove this for yourself. I mean, it works just like the level 1 case, just a little more complicated. So the thing that's not true in higher level is that, the dimension formula, the specific dimension formula we wrote down, k over 6, 4 of that. There's more on these smaller groups. It's not true that, they're generated by 2 Eisenstein series anymore. Those kind of very explicit things go wrong now. Any questions? operators? I don't know anything. You know, everything of like weight 2 has to be a generator, right? Because it can't be generated by anything else. And yeah. Maybe you can say something. I mean, you're asking about like this canonical ring of this curve, and what is it generated by? Like, there's some geometric conditions that say something. All right. So in the rest of today, I want to start talking about Hecke operators. So these are operators that have various incarnations. You can think of them on Jacobians or on modular curves, and they generate an algebra of operators, which is going to be very important for us. So first, I'm going to just talk about these things in elementary terms on lattices. So remember that L is the set of lattices inside of C. I'm going to write Z bracket L for the free abelian group on L. All right, that's kind of a weird thing, maybe. So the Hecke operator, I'm first going to define it as an endomorphism of here. So definition, n is some positive integer. Then T of n is the map from this thing to itself. So it's an additive map, so I just need to say what it is on basis vectors. And on a lattice, lambda. And they write bracket lambda when I want to think of lambda inside this abelian group. It's defined as the sum over all index n sublattices of the sublattice. And a related operator is going to be useful, but it's very easy. So for an element in C star, I'll define homothetic operator H alpha and lambda just takes this thing to the homothetic lattice. So here's the most basic result about these Hecke operators. So first of all, T of nn is T of n times T of n if m and n are coprime. Secondly, you can say something about the case when they're not coprime. So if p is a prime number, and you look at t to the p to the n, t of p to the n plus 1, you can write this in terms of the same kinds of things, but with smaller n. This is t of p times t of p to the n minus p times p to the n minus 1 times this hp. And third, these operators all commute. Tn and Tn commute. These Hecke operators are going to be pretty important for us, so I actually want to prove some of these facts about them. So let me prove this proposition. All right, so first, so if you have, so suppose lambda double prime is a sublattice of lambda of index nn. So in this quotient, lambda mod lambda double prime is a finite group of order nn. And so by the Chinese remainder theorem, it decomposes into a group of order n times a group of order n, uniquely. So there's a unique subgroup of order n. And so that's the same thing as saying that there exists uniquely a lambda prime that fits in here, where this has index m and this has index n. And so if I sum over all lattices lambda double prime of index nm, I can break this into two steps. I can first sum over my lattices of index m, and then I can sum over the index n lattices inside lambda prime. And the reason you can do this is because this lambda prime is unique given lambda double prime. But T of m lambda is the sum over lambda prime of index m, lambda prime by definition. And so when you do T of n of that, you get exactly this. Makes sense? All right, so for B, I just want to prove this when n equals 1. In general, it's kind of the same thing, but it's a little clearer when n is 1. So this is saying that, let me rewrite what we're trying to prove. I'm going to move things around a little. So n is 1, so here I have t of p squared. And I want this to be t of p squared plus p times hp. That's what we're trying to prove. All right, so let's think about t of p squared on the lattice lambda. So this is, when you do t of p, you're summing over all the index p lattices. And then you do t of p again, you're summing over all the index p lattices inside of that one. So you can think of this as summing over all chains, lambda double prime inside of lambda, where each inclusion has index p. That's just what it is by definition. And so I can rewrite this. This is the sum over all lambda prime inside lambda of index p squared of lambda double prime, but it's weighted by how many choices of lambda prime there are, right? So here you put in the number. And I can write this as the number of subgroups of lambda mod lambda double prime of order p. And so this coefficient here, so the number of subgroups, well, there's two cases, right? Because there's two groups of order z mod of order p squared. So the number of subgroups is 1 if lambda mod lambda double prime is cyclic, right? Because in that case, there's just p times this group, and it's p plus 1 if the quotient is z mod p times z mod p. Right, because then getting a subgroup is, that's like giving a line inside this two-dimensional FP vector space. You're counting the number of points on P1, which is P plus 1. Now, if I do T of P squared times lambda, that's the sum over the index 2 guys of just them with coefficient 1. So the difference is that in this case, I have p too many. My coefficient is too large by p. And I should say this case here, so this thing, this case here, if this happens, that's equivalent to lambda double prime being equal to p times lambda. Right, that's how you get that. So in this one case, when lambda double prime is p times lambda, we're too big by p. And so that's exactly what this is saying, right? I get this plus an extra p when I do p times lambda. So that's the proof of p. And now C is easy. So by part B, so C was saying that these operators all commute. So by part B, I mean inductively, this t of p to the n is a polynomial in t of p. Well, it's polynomial in, I guess, t of p and this h of p. But it's pretty clear that all these Hecke operators commute with these homothety operations. So this implies that these t of pn commute. So t of pn and t of p to the n commute. But that's all you need to do by A, because everything breaks up into coprime things. All right, so now I'm going to define an action of these Hecke operators on modular forms. So the idea is that, I mean, modular form is some function on lattices, and when I do t of n times the modular form, that function on lattice should just be, summing these the values of the modular form on these things. But it's convenient to put in a normalization factor to make things look a little nicer. So here's the actual definition. So if f is a modular form of weight k, then t of n of f on a lattice lambda is going to be, make sure I have this right, n to the k minus 1 times what you think it should be. So summing over the lattices of index n of f of n prime. And so it's more or less clear that this has the right homogeneity property. So Tn of f on alpha lambda is alpha to the minus k, Tn of f lambda. So it looks like it should be a modular form. And the only thing to check is the holomorphic conditions. And so here's a proposition which implies that it preserves the holomorphicity stuff. By now, at the moment, I'm just thinking about modular forms of level 1. So this is for gamma 1. So you can actually say what these things do on Q expansions, which makes it clear that it preserves the holomorphic nature. So if f, let's say its Q expansion is this, an q to the n. So you can write down the formula in general. I'm just going to do it for Tp, where p is prime, because it's a little simpler there. So p is prime. Then Tp of f has the following Q expansion. So you do a of pn plus p to the k minus 1 times an over p, q to the n. And here, a of n over p is defined to be 0 if n is not divisible by p. And so this shows that you're still a holomorphic function and holomorphic at infinity because you don't have any negative terms in your Q expansion. So this shows that it takes modular forms to modular forms. And okay, so let me prove this. So we want to think about the index p lattices in one of our lambda sub z's. So here's what they are. The index p lattices in lambda sub z. So this is the lattice generated by 1 and z. And so I'm going to get the lattices generated by p and z plus I for I between 0 and p minus 1. And also the lattice generated by 1 and pz. These p plus 1 lattices. And so I want to sum the value of f on all these lattices. So let's just first look at these p lattices. So I'm summing from I equals 0 to p minus 1 of f on the lattice p z plus I. And now I can pull the p out. Well, let me put my p of k minus 1 here. So I can pull this p out here, and then I can pull it out of f, and that'll come out with a p to the minus k, because f has weight k. And that will cancel this p to the k. So this is p, 1 over p times the sum from I equals 0 to p minus 1 of f. When I pull the p out, I get 1 comma, so this lattice here is p times 1 z plus I over p. And that's the lattice that I call lambda z plus I over p. Oh, maybe I should use j for this summation. And I mean, this is just what we call f of z plus j over p. Just notation. And that's what this q expansion is given, right? F of z is the sum of q to the 2 pi I over z there. So this is equal to 1 over p times the sum from I equals 0 to p minus 1 times the sum from n equals 0 to infinity of an q to the 2 pi I n times this. This is a j sum. All right, so if n is not divisible by p, then I actually have a p in the denominator here. And when I do this sum over j, I'm summing over all the p roots of unity, and I get 0. So the terms with n not divisible by p die. The sum from j equals 0 to p minus 1, I leave the 2 pi I n j over p is p if p divides n is 0 else. So taking that into account, this p is going to go away because of that p. I'm going to get the sum of p dividing n, an, and then e to the 2 pi I n z over p. And that's the same as the sum from n equals 0 to infinity of a of n p q to the n. All right, so that's the contribution of this term here. All right, and then the other term that we need is this. So f of 1 pz, well, this is f of the lattice lambda sub pz, which is f of pz. And that's the sum from n equals 0 to infinity of an q to the n p, which I can just write in terms of other notation is the sum from n equals 0 to infinity of a to the n over p q to the n. And I really should have, okay, well, I multiplied that one by my p to the k minus 1, so I was supposed to do that here. And that's why you get a p to the k minus 1 there. All right, so it's pretty simple. All right, so the point is that we get these Hecke operators acting on modular forms. They all commute with each other, so we have this huge commuting algebra acting on this finite dimensional space of modular forms. It turns out the algebra is not that big. It's a small, rather small algebra, but this lets us decompose the space modular forms nicely. And so in fact, you get a basis of the space of cusp forms at least, consisting of things which are simultaneous eigenvectors for these TP. So it breaks up the space of modular forms very nicely. And we're going to use that a lot later. And I'll say more about it as we go on, but that's kind of where this theory goes. Are there any questions?